Hello, I'm Dr. Brian Fraser, and in this video I'm going to show how to use the tool Valgrind to check the memory accesses for a C or C++ program under Linux. So to begin with, I've written a program that tries to commit as many terrible actions with dynamic memory as possible. I've loaded it up in Eclipse, and I've put together a make file. So this will build the project and all of my terrible tests here as well. Now I just want to show you what happens. I'm going to make, there's my command that actually performs my build. I named my file bad_memory.c. And so if I run bad memory, it runs like that. And that is exactly what it should do. It looks fine. There's no problems. All of the output is exactly as I had expected from just writing the code, or at least what I might have expected if I was not trying to inject certain errors into my system. Now what I could do is I could come back into my code. I can see here in my main I'm going to run these 4 different test functions, each of which is set up to demonstrate a separate type of failure. So let me go up to the top. I could look at test 1 and I could try and figure out what's going to be wrong with it. And I could look through and figure out, okay, maybe this is the problem, maybe that's the problem. But as it stands, memory bugs are very hard to find. Chances are your entire system just starts to do crazy things. Your middle of a string just changes a value randomly. Some variable that you've got just changes a value randomly, and you're not quite sure why. So let's bring in Valgrind and figure out what's going on here. So Valgrind is a tool, or in fact it's a suite of debugging and profiling tools that allow you to check your code in a number of powerful ways. The default tool, and perhaps one of the best, is the memcheck feature. And this will find a lot of different memory access problems. And the way it does this is it runs your code inside of a virtual machine. It then instruments all of the memory accesses and so forth that you're performing, and it double checks to make sure that all of your pointer accesses are valid. Now, let's start off with seeing how you'd install it. I already have Valgrind installed, but if you have sudo access to your machine and you don't have a Valgrind installed, it's going to be sudo apt-get on a Debian system, such as Ubuntu, install Valgrind. And then hit enter. You'll type in your password, and it'll go through and try and install it. So we see here that I've already got it installed. It wants to do a cleanup, but that's fine. Okay, so now that I've got it, the next thing to do is to set up your project to build correctly. You want to make sure that you build, here's my make file, with the -G option, which sets up debugging information. And that gives Valgrind enough information to instrument your system correctly and give you meaningful results when it finds errors. So I'm going to put the -G in. Now you'll also note that I have both WALL and WError turned on. This is what I normally code with, so that I let the compiler tell me as much as possible about the things I'm doing wrong. And as we saw when I build, I'll go back here and make, it finds nothing. Now I did spend a bit of time confusing the compiler in at least one case so that it couldn't find an error I was committing. But all the same, my code builds without any warnings or any errors. Plus, I also have the C99 turned on so that I can use variable declarations inside for loops. So let's go back and look at the code. So rather than me trying to walk through this and painstakingly try to identify my memory accesses, the kind of things I'd be looking for are every time I call malloc, I call free. Well, right off the bat here, I'm not calling free anywhere. But that didn't cause any failures. But let's see what would happen over time as I get a big memory leak off that. So I'm going to use Valgrind to try and trace this through. Now, let's just start off with Valgrind. What's it going to look like? Valgrind, bad memory is my program. And so when I run this, it starts up the virtual machine, it runs everything through, and all of these lines that start off with equal equal and then a number, that is a message from Valgrind to me describing something that it has found of interest. So if I scroll back up here, we can see at the very top it's got some basic, this is just, hey, Valgrind's starting to run. The number, incidentally, is the process ID, or the PID of the current process it's working on. It can trace forks. You've got a number of options to work on that. So if you're trying to debug a program that is forking separate processes, it will also help you out. And then we can see then when it starts here, it starts to tell me different errors. So for example, invalid write of size 4. So I'm writing 4 bytes to an invalid location. It'll tell me exactly where, so on bad memory.c, at line 11. So it's telling me line 11 here, I'm trying to write 4 bytes of data at an invalid location. It'll give me more than that as well. It'll tell me the actual address that I'm trying to write to, and it's inside of a block of size 3 that was allocated. So I can start to trace that through. We can see here that I've got a lot of errors though, and at the very bottom it gives me a nice display of some summary. I'm going to go back into my code and I'm going to comment out everything except the first function. We're going to walk this through one at a time. So I'm going to make, press up to get Valgrind. And so let's start at the top. So that invalid access. So it's telling me I'm trying to use some memory I don't have permission to access. Well, I can have a look at my code. So what am I doing? I'm going to create a constant for number of heights. So 3, I want to create 3 heights. I malloc some space with the number that I want here. And then I'm going to set up a loop. Well, the first thing I might do is check my loop size. So I'm going to loop from I equals 0, I less than 3, I plus plus. That looks pretty good. My access here, I access the memory as an array. That's fine. Pointers and arrays, there's a duality in C. So that looks good as well. And then I assign a value to I squared, no problems. And then finally I print it out. That should be fine as well. So we got a problem here. Valgrind's not lying to us. What's going on? Well, I have allocated 3, but 3 what? Turns out to be 3 bytes. If I want to look at what the help is for malloc, so let's do that. I'm going to man malloc. Allocates and deallocates, or pardon me, allocates and free dynamic memory here. These all are our functions. And malloc function that allocates size bytes. So I need to give it the number of bytes I want. I said 3, I don't want 3 bytes, I want 3 times the size of an int. Now I could say 3 times size, I could say, well, on my system it's going to be 4 bytes. That would work, but if I switch systems, that's not portable. So a better idea is size of int. That's one step better because now it's going to scale based on the size of an int. But even better is if I say star heights. This is the variable I'm creating. And so star heights says whatever it points to. Now, you might think, well, I'm going to dereference a null pointer here. But size of isn't actually going to run it at runtime and dereference the null pointer. The compiler subs in how big size of ends up being. So size of whatever height points to, well, I'm pointing to ints. So it's going to give me the size of an int. This is fantastic because if I come down here and I say, well, I want to switch this to a long, my code automatically updates this line of code. I can say, well, let's make this a char. I don't need to change anything else on this line of code because this is automatically scaling. Let's go back to the int. So I'm going to quit that. Let's make. And then I'm going to revalgrind. Okay. So we got rid of all those pesky errors at the top about saying we had the wrong amount of space allocated. However, down here we can say heap in use at exit. So the heap is the dynamic allocation for malloc. And we had 12 bytes in one block. So we had one thing we malloced that was unfreed at the end. It tells us a leak summary, and it knows that we leaked 12 bytes of memory. It's got some other things that maybe it couldn't trace through quite so well, and it'll give you indirect and possible leaks. But here, this is a definite leak. So we're only ever calling this function. We see malloc is called here, so I need to call free. I need to free it once. So I'm going to free heights. Let's put it here. Build. I'll clear just to make the screen cleaner, and then rerun this. We see here now there are no errors in the middle, no bytes in use at the end, no leaks are possible, and we're good. 0 errors from 0 context. So that looks pretty good. I want to show one last error here. And in fact, this will generate a runtime error normally. I'm going to move my free inside of my loop. So I'm going to try and free this multiple times. So of course you cannot free one block of dynamic memory more than once. So if I just run this, I get a normal error here from C++, or C, pardon me. So error in bad memory, double free, or corruption, which is to say that either I've already freed this memory or I somehow clobbered it with some other pointer access. It's not quite sure. Of course here I am multi-freeing it. So I'm going to put that back down here as it should be. Oops. Just to clean up the code as we go. Okay, so now if I go back to Valgrind, we're good. Life's beautiful. So I'm going to go down and I'm going to change this now to test2. Let's go up and have a look at what test2 does. Let's roll that up just for fun. So we could have a quick look at test2, but let's imagine that we wrote this code, we tested it carefully, and we couldn't find the bugs. So I'm going to make this, I'm going to Valgrind again. We'll see what happens. Invalid write of size 8. Hey, we remember what this looked like. Let's figure out what's going on. Line 26 of my code, I tried to write 8 bytes, and it tells me inside of a block of size 40 freed. Let's look at 26. What's 26 doing? Well, 26 is trying to write, it told me 8 bytes. My waits is a long, so it's trying to write one long into there. 8 bytes sounds good. But, and it tells me it was freed. So inside of a block of size 40 that was freed. So I had already called free on this. So this is a very common bug of you freed some region of memory, and then you begin to access it. These are quite dastardly because you're never quite sure who owns that memory after you freed it. So here's the problem, of course. I did all my work, and then I freed the memory, and then I began to use the memory again. So I'm going to press Alt down and reline this up so that I use the memory, and then I free it. Make again, and regrind it. No errors here, and we have one allocation, it tells us, one free. We did 40 bytes of allocated memory, but there are no problems with it. We are good to go. Okay, let's move on to test 3. I'll rebuild. Let's grind it. Definitely lost. We got 40 bytes lost in one block. Let's check out why. Well, we call malloc and we call free, so there's probably something more. Let's see if it gives us any other information. We can, incidentally, run with a leak check full option, and it will then give us much more information about where blocks were allocated and so forth. Let's just try that, see if it gives us any help. Rerun. I think I might have to move that up to the front. See if that helps. There we go. Gives us a little bit more information, and it says this was allocated by test 3 on line 32. So I can look at line 32 and it'll tell me exactly where I lost the memory. I can say, well, hang on, that doesn't look right. I'm freeing it here. But if we look in the middle, we have here this if height is null. Well, height shouldn't be null because I've allocated it up here. But of course, the issue here is that I've got single equal instead of double equal. A very common bug. In this case, my compiler would have told me about it, but I managed to suppress that by putting an extra set of brackets around it. So this is a good way to screw up your program by just doing the most simple-minded thing to make it compile. So in this case, the issue is I'm going to change my pointer to null by this line of code, and then I call malloc, which of course overwrites it. So what I might really want to do is change this to double equal. Let's walk this through slowly. Let's get rid of those double brackets there. Now when I call make, it actually gives me an error because it suggests putting the brackets around it because this looks suspicious. And in fact, this would just be a warning normally, but I've told it that I want to treat all warnings as errors. So now it gives me a bit more of a stronger warning. So I'm going to say double equals, and now it should be fine, because now I am no longer reallocating the space. Of course, inside my loop I didn't really want to do that to begin with, so I'd probably just comment that out. It's not the right kind of thing to do. Okay, and now let's go check out test number 4. Now test number 4 calls another function, so I got that here. So test number 4 is simply going to print out whatever getString gives us. So getString creates an array of size 100, and it says hello world. I'm going to create a pointer from this array. Now this step is kind of useless. We'll see what that does in a minute. And then I'm going to return the pointer. So that looks pretty good. I'm not even using dynamic memory here. Let's see if anything happens. So if I just run this, bad memory, wait, that doesn't look quite right. It's supposed to say hello world, but it came out a bit garbage. In fact, when I run it a bunch of different times, it comes out garbage every different time. So that's kind of funny. So that's your hint that something is wrong. Code that shouldn't be giving me different answers is. Let's try and trace that through. Now I could think about this and try and reason through it. Let's see what Valgrind is going to do for me. Let's run bad memory through Valgrind, and up here it says conditional jump or move depends on uninitialized values. So that seems kind of weird. Now this is inside of vfprintf, which is called from printf, which is called from test 4. Now anytime that you've got a statement like this, it's sort of a red flag. Yeah, sure, it looks like printf is doing the bad thing, and you might think there's a bug in clib, which there could be, but here it's not so likely. We can see here, line 49, of course, is my printf statement. Here, there's something going awry. It's trying to read from uninitialized memory. So it's probably moving data into to print out to the screen. And we can see it does this all the way down here, the IO file, and so forth. Params to write points to uninitialized bytes. So it's done a fair number of things. It looks like it got a lot of different bugs. This actually stems from just one issue. And the issue is that I am beginning to use the stack. So this is just running off the stack, and I'm passing in an address off the stack. Now, really what I want to do here, as I tried this to start with, is I want to return message. But, let's get out of this. GCC is smart enough to tell me, hey, you are returning, your function is returning the address of a local variable. Now this again is a warning. It's just a warning. But that's really, your house is on fire. It's just a warning. Because this is going to sit on the stack. And when I leave the function, it gets popped off the stack. And so this pointer becomes invalid after I leave this function. So then print out I get a pointer to memory. It looks good, but of course it's on the stack and I don't have access anymore. So that's what we're getting here. Valgrind can help us trace that through. So after I've gone through all and fixed all of these bugs, my program should then run without any errors or any warnings, or should compile without any errors or warnings, and Valgrind should also come up and show me that everything is fine. Alright, thank you for watching.